Hello, everyone. So this is Group 18 presenting for the Robotics 530 Mobile Robotics course, and our topic is LLM-based path planning for low-light conditions using ORBSLAM. This is presented by Kaushek Kumar, Sanjana Raghavan, and myself, Vishwa Mehta. When deploying autonomous vehicles in low-light environments, we face several challenges like poor feature detection, increased localization errors, and reduced map accuracy, which leads to unreliable navigations under dynamic lighting conditions. To make the autonomous vehicles deployable in industrial warehouses and disaster response situations, they need to be able to detect reliable features and produce accurate maps in dynamic lighting environments. Mission delays, safety risks, and the time and energy costs involved necessitate the need for a robust, adaptive, and intelligent navigation system that can enhance the visual output, understand high-level goals, and plan and execute safe paths in real time. For this, the proposed solution is one that can handle efficient waypoint generation, optimize trajectory planning, and high-level context-aware decision making. For this, we use Learning for the image enhancement. We use ORBSLAM for the robust mapping, leverage the LLM-based waypoint planner plus D Lite for path planning, and execute the trajectories with MPC controller. The first image enhancement architecture that we experimented with was Enlighten GAN, where GAN stands for Generative Adversarial Networks. It was chosen due to its capability of being trained in absence of paired unpaired data, which makes it convenient for developers. It works with the help of a dual discriminator setup that works on global and local illumination separately, resulting in preservation of semantic and structural details while controlling the overall exposure. However, the model proved to be computationally expensive, and the SLAM algorithm ran with zero point 0.5 to 1 FPS, which is troublesome for online computation. To aid this, we moved to using Learning, that stands for Self-Calibrated Illumination Learning Framework, which is a lightweight model that uses only one convolution block during the processing. The self-calibration is enabled by modeling illumination through a cascading of different layers that share the same pre-trained weights, making it a one-step process. Hence, due to the robustness of this model, we use Learning for the rest of the project. What do you, Kaushik?
So now I'll be presenting regarding the methodology of ORBSLAM 3. So we start by using ORB features that's oriented fast and rotated brief method. So which is a feature extraction method to detect and track visual features across frames. This enables accurate estimation of camera's motion over time. So ORBSLAM 3 supports multiple sensor types including monocular, stereo, RGBD, and it builds a sparse 3D map of the environment in real time. So in our use case, we are using RGBD data for recording or capturing the sensor information. Now, the next step is to enhance the image using Learning framework. So to improve performance in low light or challenging visual conditions, we integrate the image enhancement module. This boosts contrast and reveals more detail in darker frames. So these enhanced frames are then fed into OBSLAM 3, which results in more stable feature tracking and improved pose estimation. And finally, we project the 3D point cloud generated by the OBSLAM onto the 2D ground plane to build an occupancy grid map. So this map is further annotated with semantic segmentation, semantic object positions, enabling downstream tasks like autonomous navigation and path planning. So as you can see, we are displaying the OBSLAM 3 results in this slide. So first thing, the bot is moving in the gazebo environment that we have provided, and the image is being fed, the RGBD image is being fed to the OBSLAM 3 architecture, where it extracts the key points and it builds the sparse point clouds from the key points that it generated. So after generating this, it'll be producing an entire map out of it.
So in this slide, I'll walk through our LLM-based navigation pipeline. The process starts with a high-level JSON command that specifies the source object, target destination, and any safety constraints like obstacle margins or waypoint spacing. We pass this command alongside the robot's current pose and the semantic map, which includes labeled object landmarks. These elements are embedded into a structured system prompt that also includes occupancy grid map. This prompt is sent to a locally hosted Llama 3.1 model via Olama, which generates a series of straight line waypoints. One of the key advantages of using an LLM is its semantic awareness. It can prioritize certain regions or avoid others based on object labels and contextual understanding. Each generated waypoint is then validated against the occupancy grid to ensure compliance with spatial constraints. If a waypoint violates safe margins or lies in an occupied cell, we automatically requery the LLM with an updated context. The refined set of waypoints is passed through a D-star light planner, which treats these waypoints as soft subgoals. D-star light computes a globally consistent obstacle-aware trajectory that can locally deviate from the original LLM path if needed. Finally, the robot follows this plan using closed-loop control. Its pose is updated continuously, velocity commands are sent via an MPC controller, and the system invokes incremental D-star repairs in real time if obstacles are detected or deviations occur. This combination of semantic reasoning and dynamic replanning ensures interpretable navigation in complex environments. Next slide. In our test runs, the LLM waypoint suggestions consistently matched with the intended semantic routes. Now, navigating correctly around scene elements to reach targets. When the LLM couldn't propose a multi-point path under tight constraints, it gracefully fell back to a direct straight line instruction, and the robot still completed the task. We also observed that the D-star light component handled dynamic changes robustly, repairing segments on the fly without returning to the LLM. From an from an interaction standpoint, every full planning cycle felt responsive, supporting on the fly adjustments rather than long pauses. Looking ahead, our next step is to refine the prompt so that the LLM can output curved or spline based trajectories, and to also include motion primitives that better respect the robot's kinematic limits. Thank you.